Hey everyone, and welcome to the Null channel. Are you guys ready for something just a little bit different? I know I do a lot of stuff on Kubernetes, and don't worry, that's going to continue. But recently, I've been digging into how databases work, and I'm still far from an expert, trust me. But I thought, hey, let's go ahead and build a database bit by bit and share it with you guys and share what I learn. Before we start, I had two massively huge inspirations. The book Designing Data Intensive Applications by Martin Kleppmann. The book is absolutely fantastic and really is a must read for just about anyone interested in writing software in 2022. It's really quite fantastic. But not only that, over the winter months, I had the absolute pleasure of watching Ben Eater's content where he builds an 8-bit processor bit by bit, and he takes on a new issue every single episode. And it's absolutely fantastic. I have linked both of those things in the description below if you guys would like to check it out. On top of this, I've been struggling with how to better show information and enhance the learning experience. So welcome along the ride for something just a little bit different than you're normally accustomed to. So let's get into it. Let's start building a database. So if understanding how the choices at the data layer abstraction affect your abstraction, your application that's data intensive, or understanding the different approaches and issues that must be solved when maintaining consistent data on disk, then go ahead and join me. If you would rather only see content on Kubernetes though, don't worry, I'm going to continue to make those. This is just something I'm interested in understanding better, and I thought that, you know what, I should just go ahead and share my learnings with you guys as I learn the content myself. So the very first issue we need to do is to actually store and write data to disk. And it turns out this issue is actually kind of a hard one. It also turns out that the OS does not really protect you from doing something kind of dumb. And it's going to make it quite easy to either lose or corrupt data. And if you have corrupted data, that's kind of losing data. But don't worry. I built some demos, and I'm going to not only show you the right way, or a possible right way, but I'm also going to demonstrate how you can do the bad ways and what it looks like, and you're going to get to see all that, and it's all open source, so you can go ahead and check it out. The really, really cool thing is the solution to all these hard problems is actually quite simple and brilliant when you think about it. But as all simple solutions, it has some of its own quirks that we'll have to deal with in subsequent videos. So what are the problems with saving data to disk? Well, the main one is making sure you don't lose data. I know it sounds obvious, but that's the main one. So writing to disk does not have to be atomic. It depends on what the underlying hardware really is. For example, if it's NVMe, the spec itself guarantees sector writes autonomously. But now you need to ensure that you're running on NVMe, but you also have to be making sure that you write to a single sector. Or if you have to write to more, then that's not atomic. But then again, how many databases limit themselves to a single type of hardware? And the problem gets even worse when something like network-attached storage is introduced, as not only do the protocols vary, but the drives that are attached on the other end do as well. Now, to be clear, there is a whole lot around this, and to make a truly blazing fast data storage engine, you're going to need to learn and know and understand what the capabilities of the underlying hardware are, because there is a cost associated with ensuring write autonomy. And if it's not done at the hardware level, it has to be done on another higher level in software, which incurs a cost. But guess what? We're not going to worry about write block sizes just yet. Those will be in future episodes. So needless to say, if we're trying to update a value, we cannot just write the new data over top of the old data. Well, I mean, you could, but it would require a buffer to write, and this is kind of slow as you're kind of double writing. Or at least we can't do it without wondering if we might lose the data. Not only this, if the new data is not the exact same size, it might not even be possible to write the new data in the same place on the drive anyhow. So if this write was to fail in the middle of writing, then only half of the data has been persisted to disk due to a power failure or something like this, the data would now be corrupted, as not only would we not know what was originally there, but we would also not know what the new value was either. And this is how you get into data loss or corruption. Anyhow, this sounds really complicated, but we have a really simple solution to this. To deal with this really hard problem, the simple solution is just to keep a log. And this is why it's called a log-based database. So instead of updating the old record, we just instead write a new value to disk. That way, if something happens while writing the new log entry, like a process crash or a power failure, the client trying to store the info in the database will get disconnected without getting an OK response. And in this way, it's going to know that the value was not saved, but just based off of the network protocols. But more importantly, if it only wrote half of the record, it does not matter. It did not stomp on the older record, so no data was actually lost. Well, none other than the failed write that you attempted to write. How can we tell if only half of the record was written and it's not a full record? Well, don't worry about that just yet. We will deal with that in a future video, but not in this one. So now we have an idea of what exactly a log-based database is and how it works. I mean, it's just a log of records like you would find in your microservice. But it has some really cool and interesting aspects about how we recall and delete data. So you know what? Let's write some code and implement the simplest log-based database we can. It has some really simple and interesting concepts to let you update and delete values. And then in subsequent videos, we're going to build on this super simple database and give it more features and make it even better. I really quickly made an HTTP REST-ish API for our database. It's not a good API design. This is just here to quickly let us communicate with our database while it runs. We have a put, get, and a delete call, and it's really all we need to do for now. There is nothing special here. Don't worry, we can and will change it in the future. This is just a simple start. Later on, we can look at what it means to implement a document or graph API. They are all just built on top of your data storage engine, the thing we are starting to build now. Let's just really quickly review the API as it stands right now. Get requires a key. This key corresponds to the data we wish to retrieve. The post takes a key, but it also takes a value. This lets us write the value for the key in the database. Interestingly here, we will not have to specify if this is an update or a new value, but we'll get more into that in just a second. It's one of the really cool things about a log-based database. The last one is delete. It also takes the key and lets us delete the value for that key. Super simple stuff here. Nothing really that interesting. And this is the basis for our application. Now again, before we move on, I know, yes, this is bad API design. It should have a version and there should not be root paths here. I get it. These set of videos is not on good API design. This is just a means to an end. So please, let's not get hung up on the API design right now. We will be updating this in the future when we have a few more features and want to implement a real API to store and access data. Let's not worry about all of that for right now. That is probably its own set of videos, and this is agile. We're taking it at one step at a time. All right, before we can run this, we're going to need to register our functions with our HTTP server. Well, actually, we're going to need to create an HTTP server and then register a new service to it like this, and we'll just bind all of that to port 8080 for right now. And again, we're probably going to have to pass in through a config file at some point to configure this stuff and other aspects of our database, but that is not this day. Let's run this and test out the API. You can use something like curl if you like and just make simple requests like this. But to make your and my life a little bit simpler, I made a little command line app that makes requests against the API, letting you make simple and easy requests to and from the database. I guess you could really consider this to be our first client library, technically. Furthermore, I created a load testing part of the CLI that lets you generate load for the API, so if you want to sit back and watch the server work for you, you can. This is a great way if you're trying to implement your own and following along with these videos and want to test your database and your API server. It's really actually quite useful, and I found it useful myself. So there are three main things that we want to do. For today, it's reading, writing, and deleting. With writing, there are really three types of writing events. The first is writing a new key and value. The second is when you're updating an existing key with a new value. And the very last writing event is also one of our main objectives, deleting a key and value. And yes, deleting is writing to the file. All three of these can cause data corruption or loss if you're not careful. And one of these, actually, interestingly enough, can cause a deleted record to come back to life as a zombie. But more on that in just a bit when we're talking more implementing delete. So we're making a log-based database, right? So writing a new key and value is just appending a new line to our log. Not only is this quick and easy, but it's also pretty safe. Well, okay, almost safe. Before we implement this in code, let's talk about the one way writing to a file could go very wrong very quickly. While eventually we are going to enable multiple threads to be used to get and write data, for right now, it's best for just a single thread to write to a file at a time. While our app is multi-threaded, we will be forcing only one thread at a time to touch the file for writing. Don't worry, reading can read as many as they want. Don't understand why this might cause you trouble? Don't fear, I made a little demo app to show you just why this might be a bad idea. In the repo with the database, you will find a folder called Experiments. And in this folder, I have an experiment called Multi-Threaded Single File Disk Write. And in it, I spin up over 100 threads and write the same line to a file with the thread number. If this was safe, each thread's data would print a clean line of data to the file. It would not necessarily be in the same order as we started the threads, but it would at least be clean. As you can see, this is by far not the case. And this would not do for our database to get jumbled like this because this is data corruption, and it's generally frowned upon in databases, or really frowned upon in anything, I guess. I included this code in the repo, so you're all more than welcome to see how your OS handles this, but safe to say, we don't really want this. Let's do this code now. First, we get a write lock for our file. As previously mentioned, we don't want to corrupt our database by trying to write to it at the same time with multiple threads. Don't worry, we will be using multiple threads later in this series. It's just easier right now to keep writing lock to a single thread for the time being. Again, if you like this and want me to continue to tackle the problems like this using multiple threads in a database, please like the video and let me know in the comments, as I put a lot of work into this, and even this simple introduction video required an enormous amount of work on my part. So anyways, if you'd like to keep seeing these, please let me know, and it really means a lot to me. All right, back to writing the code in the database. So once we have a write lock, all we have to do is append a new line to the log file. It's really, really easy. Rust gives us easy commands. Every language has an easy way to do this. And for the time being, we're just going to append a new line with the format of key:value in absolutely plain text. And again, this is not the best, and there will be more information we need to store with a record, like it's going to be called database metadata. And on top of that, plain text, while it's nice for humans to read, is not really the most efficient to store data in. But remember, we're going to solve one problem at a time, and this is all the code you need right now. It's just that simple. At this point, we could implement our get function and just find the right key and return it. But before we do that, let's implement the updating value, as that's where it actually gets really interesting, and it's going to affect how we read. Well, to be honest, we don't have to do anything. We just write a new line as if it was a new key and value. This means that for any single key, there could and should, or maybe are, multiple values in our log. This is okay, because when we get a record, we start at the end of the log and work our way backwards up the log, reading from the newest record to the oldest, returning on the first record for this key. Or, to be more accurate, the most recent record. This will ensure that we get the correct and most up-to-date record when getting a record. So we don't really need to update the post function at all, and we avoid all the complexity of trying to update a record on disk. Let's jump back to our read function and implement this. First, we're going to need to get a read lock, as we can have a lot of readers at once, but we can't have someone writing while reading. Once we have a read lock, we can now safely start reading the file. Now, interestingly, again, here, we don't want to read this line by line. We want to read this line by line backwards, because remember, our latest value is the right value. Thankfully, there is a project that already does this for us in Rust, and I'm sure there is in your language as well. This lets us quickly get to the end of the file and read its contents backwards line by line. If you remember correctly, each key can have multiple records. It's just the latest record that is the correct record and the one we want to find. Now here, all we have to do in the code is keep going backwards, reading each line by line, breaking the key value out and comparing it to the value we are looking for. And if we find it, we can stop and return it. The cool thing here is with Rust is as soon as the variable that is accessing our file goes out of scope, it's going to go ahead and close the file as well. This is one of the super cool features of Rust and pretty much lets us not worry about our open file or even the lock holding it open. They will all close at the end of scope. But again, you should be able to implement this in any language you want. And I'm thinking about, after doing this, writing a Rust class if you guys are all interested. Okay, so that was pretty simple. Not many lines of code here. The solution to updating was just not to update the value. Who would have thought of that? It's awesome. We did not have to worry about all the issues of updating data in place at all. Now, deleting has some side effects as well, and some of them will require follow-up videos to fix. But for today, we're going to keep it super simple. We could lock the entire log, the entire file, look for each and every instance of the key, remove it, and write the whole log file back. In this case, you can't just look for the latest record, because if you deleted that one, then when you called get again, you would actually get an old or stale record, or a zombie record, because it came back to life after you deleted it. But oh boy, does that seem like a lot of work. Not only is it a lot of work, but it also requires getting an exclusive lock of the entire database while we scan for all the keys that are possibly there. While this might not be a big deal right now, as we only have a few values in our single log file, but as our database grows in size, this is going to become much longer and it's going to become a very expensive operation. And because we don't want really large files and things like that, as well as disk sectors, we're actually going to be breaking this log file up into smaller chunks in future videos, meaning that it's not actually a tenable solution to lock the entire database. Plus, it just turns out that there's an easier way, and why wouldn't you just do the easier way? What if we could do the exact same thing as for writing a new value? Yeah, let's actually just write a new line. And now I know that you're asking me, how do we delete something with just writing a new line? We can't just write a key with no value, because no value could be a valid value. So while a real solution would be to have record metadata and to write this information to the record's metadata, right now, since we don't have metadata, and that will be implemented in a future video, we're just going to write a special value tombstone. At this point, we need to update our GET request again to return no record found if it finds the key but has this special tombstone as a value. So for delete, we will just do the same thing in the code as we did for post. It's really just copy and paste, but instead of writing the supplied value given with the post function, we will write our own special value. This will also cause us to need to update our GET request for the database. As in the GET request, we will need to check the value for the retrieved key to see if it equals the tombstone, and return no value found if it is a tombstone that was found. And this is just beautiful in its simplicity. Now, this is a fully functioning database. Now, you might be thinking that this database has a few problems. And you would be right. The first is that the database is going to be a lot larger than the amount of data you're storing. Now, that sounds weird, but it's true. And why is, well, because look here at this file. I changed the value 4 or 5 times and it never deleted the old records. But not only that, I then deleted the record. And if you look here, the delete actually added extra storage instead of cleaning it up. Whew, this is not real great, and we're going to have to fix this. Another thing you might have noted here is that one file is going to get very, very large. So we're going to need a way to break it up into smaller pieces. There's actually a few reasons we want a smaller log files or chunks of data, but being a log, that is going to cause its own set of issues, and we're going to have to deal with those one at a time. And lastly, the really acute of you are going to point out that if you request a value that does not exist in the database or has not been written to for a while, you will have to scan the entire database from the latest record to the oldest record before either finding it or not finding it. And this means that GET requests for values that don't exist will get longer and longer the larger the database gets. And being a single file log, this will get quite long quite quickly. And while we use read-write locks, when the write lock requests its lock, it's still going to have to wait for all the concurrent readers to finish reading. Meaning you could hang waiting for a very long time when reading a value that does not exist in a single file that is gigabytes in size, or even terabytes. Yes, our database should be able to support terabytes. Maybe not today. All right, so quickly, before we go, let's make sure all this code works. While you can just use wget or curl or whatever you like, you can also just use the command line tool I wrote to write values and return them. But even better than that, because we are currently just storing everything in plain text, you can go ahead and check the database file and see all of your values in real time. This is actually pretty cool, but something we're going to have to fix in the future, as it's not the most efficient way to store data in plain text. It turns out that's not real great. So to help understand how all this works, let's actually watch the database run. So first, let's insert some data. As you can see, each time I insert a new record, even if the same key already exists, a new record gets appended to the end of the log. Super cool. Let's get the record for the key Merrick. As you can see, there are actually 2 entries, but it only is going to return the very last one, as that's the most up-to-date record. Awesome. Now, let's delete the record for Merrick. And look there, it actually just added a new line with the value of Tombstone. Now, when we call get again, check it out. The database says it doesn't actually have the record, even though it's obviously there. Cool thing here, we can actually go in and manually edit the database, delete the Tombstone, and poof, we get our record again. So that is the basics of a log-based database. Now, we are far from done. We still have a lot of issues left to solve. Some of the issues we're going to solve in the next video revolve around breaking this one large singular database file into smaller chunks. This will actually solve a lot of issues for us. And while I'm not going to get into all of the issues these smaller files solve and some of the problems they create right now, I did want to let you know one that you can be thinking about before my next video on the subject comes out. And that's compaction. Compaction is kind of like the managed language garbage collector. Know how we wrote all of those duplicate keys and we just wrote a tombstone to delete the object, but then the object was never actually removed or deleted? Well, we really want to compact these log files and delete the values, as our database will be filling up with old, stale, and deleted data over time. You can kind of think of compaction as either the garbage collector or the disk defragmentation. With a single large file, we would have to lock the entire file, hang the entire database, and read that entire file into memory to compact it. Splitting this up will enable us to start managing this process in smaller, more manageable files. It's even going to let us continue accepting writes, all while cleaning up the database, meaning we will not have to lock the we won't have to lock the entire thing. So if you want to learn how that is done, if you want to join me in writing some more code and understanding how databases work at a kind of a lower level, just a little bit better, please hit that like button and let me know that you want to see more videos like this. But that's it for me today. If you have experience in databases and would love to share it, leave a comment and a post below. If you have ways to make this better, post about it. We can all learn from everybody together. And I'm going to keep making videos tackling more issues one by one on the null database. Thanks for watching, and have yourselves a fantastic week. And if you did not like this video and do not like understanding how databases work at just a little bit of a better level, go ahead, hit that subscribe button, stick around, and see all of the awesome content you're missing. That doesn't even make any sense. Have a fantastic week.